Microeconomics for Investors. Chapter 9, Productivity and Efficiency. Section 1, Productivity Drivers. Productivity improves when a business gets more useful output from what it already has. That can mean producing more with the same workers, machines, and materials, or producing the same amount with fewer hours, less waste, or less capital tied up. For investors, this matters because higher productivity often lowers cost per unit, which can support margins even in competitive markets. A factory that makes 100 units with 10 labor hours is more productive than one that needs 15 hours for the same result. The same logic applies in services, where output might be customers served, claims processed, or deliveries completed. Over time, firms that steadily improve productivity tend to build stronger cost positions and more durable profits. Most productivity gains come from a small set of recurring levers. Capital investment can raise output by giving workers better tools or more capacity. Labor quality matters because skill, training, and experience reduce mistakes and help work move faster. Technology adoption can streamline routine steps, while management practices shape scheduling, coordination, and workflow. Economies of scale add another source of gains by spreading fixed costs across more output. The key point is that these levers do not matter equally in every business. The right one depends on what is currently holding performance back. The smartest productivity improvement usually starts with the bottleneck. If one machine keeps failing, hiring more workers in other parts of the plant may do very little. If a service business has high employee turnover, buying new software may not solve the real problem either. In manufacturing, the constraint is often equipment, capacity, or process speed. In service businesses, the limiting factor is often staffing, training, scheduling, or supervision. Investors should be careful with management claims here because spending in the wrong area can look impressive without producing much real output gain. Capital and labor improve productivity in different ways, and it helps to separate them. Better equipment can raise output per hour by making each worker more capable, faster, or more precise. But capital-heavy improvements also create fixed costs, so utilization becomes critical. Expensive machines only pay off if they are used well. Labor improvements work through skill, judgment, and execution. Well-trained employees make fewer mistakes, solve problems faster, and often use materials and equipment more effectively. The catch is that training rarely shows instant results, so short-term numbers can look flat before gains begin to appear. Technology and management often create productivity gains without adding much headcount. Software can automate routine tasks, improve visibility, and reduce handoff errors, while better management can improve scheduling, priorities, and accountability. That means the same people and machines may produce more simply because the work is organized better. Still, implementation usually comes with friction. A new system can slow output for a while as employees learn it and workflows are adjusted. This is why strong resources alone are not enough. Poor management can leave good labor and good equipment underused. Scale often helps productivity at first because fixed costs are spread across more units. Rent, equipment, and overhead do not rise one for one with output, so average cost usually falls as volume grows. That is why a larger plant or platform can often serve customers more cheaply than a small one. But scale is not a free lunch forever. As operations grow, coordination gets harder, layers of supervision increase, and complexity can start to offset the savings. Past a certain point, diseconomies of scale can appear, and the business becomes bigger without becoming better. To measure productivity, start with a simple baseline. The core formula is output divided by input, but both parts need to fit the business you are studying. Output might be units produced, customers served, deliveries made, or even revenue in some contexts. Input might be labor hours, machine hours, or another scarce resource. The value of the metric comes from comparison, especially before and after a change. If output rises from 50 units to 60 with the same labor hours, that is a clear productivity gain worth understanding. In practice, productivity gains often come from several complementary changes working together. A furniture shop might install programmable saws, but the equipment alone may not deliver much unless workers are also trained to batch jobs more efficiently. There is usually a settling period as people adapt and the process is refined. During that phase, managers need to measure useful output, not just activity. More cutting time does not matter if defects or rework rise. When the changes fit each other, a business can move from something like 50 chairs in 200 hours to 80 chairs in the same 200 hours, which is a meaningful jump in labor productivity. Even successful improvements usually run into a new constraint somewhere else. A trucking firm may add routing software and improve dispatching, which increases deliveries from 240 to 280 per day. That is a real gain, and it shows better use of labor and fleet time. But if part of the fleet is old or incompatible with the new system, those vehicles can cap further improvement. Productivity is often a moving target like this. Solve one bottleneck, and another becomes more visible. For investors, that is a reminder to ask not only whether results improved, but what now limits the next round of gains. A few common mistakes can make productivity analysis misleading. One is focusing only on labor hours and ignoring materials, quality, or machine utilization. Another is judging a change too quickly and forgetting that learning curves often create a temporary dip before improvement shows up. It is also easy to confuse activity with output, especially when a team looks busy but produces little usable work. And finally, businesses rarely improve through one lever in isolation. Equipment, training, process design, and management usually interact. Good analysis looks at the whole system and gives changes enough time to prove themselves. Section 2. Labor efficiency. Labor efficiency narrows the focus from total productivity to worker time specifically. It asks how well labor hours were converted into completed output by comparing the hours that should have been needed with the hours that were actually used. That makes it especially useful for diagnosing time-related operating problems. A weak result does not automatically mean workers are underperforming. The issue may be delays, poor layout, missing materials, or unrealistic staffing. It is narrower than overall productivity because it isolates human work time rather than combining labor with machines, energy, and materials. For managers and investors alike, that narrower lens can be very helpful when labor is a major cost or a key constraint. Labor efficiency depends on two numbers, and both have to be credible. The first is standard hours allowed, which reflects how much labor time should be needed for the output actually completed. The second is actual hours worked, which is the real time spent on the job. Standards usually come from time studies, engineering estimates, or past operating history. But if the benchmark is set too tightly or too loosely, the ratio becomes misleading. A business can appear inefficient simply because the standard is unrealistic, or appear efficient because the target was too easy. The formula is straightforward. Labor efficiency equals standard hours divided by actual hours. A result of 10 or 100% means labor time came in exactly on standard for the output completed. A result above 100% means the team used fewer hours than expected, while a result below 100% means it used more. That interpretation is useful, but it should not be taken too mechanically. Very high efficiency can sometimes reflect skipped steps, quality problems, or unsafe pacing rather than a true improvement. The number is a signal, not the full explanation. A correct labor efficiency calculation starts with a clear standard time per good unit. Then you multiply that standard by the number of good units actually completed to get standard hours allowed. After that, you measure actual work time carefully and make sure it matches the standard's definition. If breaks are excluded from the standard, they should be excluded from actual hours too. Most important, only good output belongs in the calculation. Defective units do not earn standard hours just because labor was spent on them. Consistency in time tracking is what turns this from a rough guess into a reliable operating measure. Consider a simple example. A team assembles 50 units, and the standard is 0, 5 hours per unit, so the standard hours allowed are 25. If the team actually uses 30 labor hours, labor efficiency is 25 divided by 30, or about 83%. That means the process required more labor time than expected for the output delivered. The extra 5 hours might come from rework, bad workstation layout, missing tools, or interruptions in material flow. The metric tells you there was excess labor usage. The next step is to investigate why. When labor efficiency falls, the root cause is often wasted process time, rather than workers simply moving too slowly. Teams may be waiting for materials, searching for tools, or redoing work, because earlier defects were not caught. Training gaps can also matter, especially when people hesitate or need extra supervision to complete routine tasks. Overstaffing creates another hidden drag, because idle workers still count in labor hours even when they're not adding output. Fatigue and low morale can lower performance too, especially in repetitive or poorly managed environments. So a low ratio should prompt process questions first, not blame. This warehouse example shows how the calculation works in a real setting. A labeling team has a standard of 3 minutes per good label and completes 100 good labels, so the standard time allowed is 330 minutes. After excluding the 30-minute meal break, actual working time is 390 minutes. Dividing 330 by 390 gives an efficiency of about 84, 6%. That tells us the team used more labor time than the standard for the output produced. The useful follow-up is not to stop at the percentage, but to ask what caused the extra time, such as material delays, poor layout, tool issues, or fatigue. The real value of labor efficiency comes after the calculation. A weak result should push managers to examine whether delays were avoidable, whether staffing matched demand, and whether training or layout problems are slowing work. A strong result should also be checked against quality and safety, because faster is not always better if defects rise or workers are overstrained. This is why the metric should guide decisions about workflow, not become a score to chase in isolation. Looking at several periods is especially important. 1 month may reflect random disruption, but a steady trend is much more informative. Here, the small assembly line completes 15 good units at a standard of 2 hours per unit. That gives 18 standard hours allowed. The team records 22 total hours, but 2 of those are paid breaks, so actual work time is 20 hours. Labor efficiency is therefore 18 divided by 20, or 90%. The result is below standard, but not dramatically so. It suggests some excess labor time that could come from minor delays, rework, layout problems, or small equipment stoppages. Labor efficiency is only useful when both the math and the interpretation are sound. One common mistake is mixing paid time with actual work time, which can distort the result immediately. Another is counting defective output as completed output, even though defects do not create real value. Outdated standards are also dangerous, because they can make current performance look better or worse than it really is. Just as important, managers should avoid blaming workers too quickly when machine downtime, poor scheduling, or training gaps may be the real cause. And the metric should always be read alongside quality, cost, safety, and worker well-being. Section 3. Automation. Automation means using technology to complete tasks with little or no direct human intervention. In business, that usually involves software, sensors, workflows, and decision rules working together to handle structured tasks. This is broader than simply replacing physical labor with machines. Mechanization may reduce human effort, but automation goes further by controlling steps, applying rules, and moving information through a process. It works best when tasks are repetitive, predictable, and clearly defined. A good example is invoice processing, where data can be captured, checked, routed, and recorded with only exceptions sent to people. Businesses automate mainly because they want higher productivity. A well-designed system can process work faster, produce more consistent results, and handle rising volume without needing a proportional increase in labor. Manual work often slows down when demand jumps, and quality may vary from one worker or shift to another. Automated workflows reduce that dependence on repeated human effort. They also avoid fatigue and can operate with greater consistency over time. For investors, the attraction is not just lower labor need, but a process that can scale more smoothly as the business grows. Automation is not one single thing. It exists on a spectrum. At the simple end, task automation handles one narrow activity, such as sending an automatic reply or copying data between systems. Process automation is broader and links several steps together, like matching invoices and routing approvals. More advanced forms, sometimes called intelligent automation, adapt to changing data patterns and can support tasks like fraud detection or exception prioritization. The lesson is that complexity should match the process. A narrow, repetitive task usually does not need a highly adaptive system, and using one may add unnecessary cost and risk. Automation is a good fit when the underlying work is stable and easy to standardize. High-volume tasks with repetitive steps Rule-based decisions and digital inputs are usually strong candidates. In those settings, the system can repeat the same logic thousands of times with speed and consistency. But if the process is messy, full of exceptions, or poorly documented, automation may only make the confusion happen faster. That is why process mapping comes first. Before automating, a business should understand the workflow clearly enough to explain where the rules begin, where exceptions appear, and what success looks like. Successful automation projects usually follow a disciplined sequence. First, the business maps the current workflow and simplifies it where possible. Then it chooses a tool that fits the task, whether that is a simple software bot, a workflow platform, or a physical robot. After that, clear rules are built into the system so routine cases can be handled consistently. The project should then be piloted carefully because edge cases often reveal problems that were not obvious in planning. Even after launch, monitoring and maintenance matter, since the process, inputs, or business rules can change over time. Automation can deliver strong efficiency gains, but the full economics are wider than the upfront purchase. Software, hardware, integration, and training all add to the initial cost. Then come the ongoing expenses of monitoring, debugging, updating, and maintaining the system. If business rules change or regulations shift, a rigid automated process may need redesign. This is why a project that looks cheap at the start can become expensive later if support costs are ignored. Investors should evaluate lifecycle cost, not just build cost, when judging the real payoff of automation. People usually remain essential even after automation is introduced. Their role often shifts away from routine repetition and towards supervising systems, handling exceptions, and improving the process itself. That matters because real business environments rarely stay perfectly predictable. Unusual transactions, missing data, customer disputes, or policy changes often require human judgment. Oversight also reduces risk by catching failures that automated rules may miss. In many cases, the challenge is not eliminating labor but retraining it, so people can move from doing the task to managing the system that now does most of it. This logistics example shows the potential very clearly. A company processes 500 delivery confirmations each day, and automation cuts the time per confirmation from 3 minutes to about 20 seconds. Errors also fall sharply from 4 to 0, 3%, which means the gain is not only speed but accuracy. With that kind of improvement, the payback period can be very short, in this case, less than 4 months. But the story does not end with the software doing everything. People are still needed for escalations and unusual cases, which is exactly where human judgment adds the most value. Automation tends to disappoint when businesses make a few predictable mistakes. One is automating a broken process instead of fixing the underlying workflow first. Another is ignoring maintenance costs and treating the project like a one-time investment. Some firms also remove too much human oversight, which can raise risk when exceptions appear. Tasks that are highly variable or dependent on judgment are often poor candidates as well. The best results usually come from selective, disciplined automation of a few well-suited steps, rather than from trying to automate everything at once. A practical way to build judgment here is to look for one task that is clearly repetitive, digital, and rule-based. Invoice data entry is a classic example because the manual steps are easy to describe: open the invoice, copy fields, validate vendor and coding, enter the system, and confirm the record. Once those steps are visible, you can ask what tool might automate them, such as OCR combined with workflow rules or an API connection. But a good proposal also names the limitations. File formats may change, exceptions may arise, and some human review may still be needed. The goal is not just to spot a possible automation, but to explain why it is a strong candidate and where it could fail. Section 4. Innovation Impact. Innovation matters to investors when it improves measurable performance. The important question is not whether a process or product sounds advanced, but whether it raises output from the same inputs or maintains output with fewer inputs. Sometimes innovation improves physical efficiency directly, such as reducing setup time or waste. In other cases, it improves quality or customer value, which can support better pricing and stronger revenue per employee. Automation is only one form of this broader idea. What investors should look for are outcomes like lower unit cost, fewer defects, higher output per worker, or greater customer value created from the same resource base. It helps to distinguish process innovation from product innovation. Process innovation changes how work is done, and it often improves efficiency directly by raising throughput, reducing defects, or lowering cost per unit. Product innovation changes what customers buy, which may not alter factory speed very much, but can increase demand, pricing power, or revenue per employee. Both can be valuable, but they work through different channels. A company with better production methods may gain a cost advantage, while a company with a more attractive product may gain a revenue advantage. Investors should be careful not to lump the two together, because the economics and the risks are different. One of the most important effects of innovation is that it can expand a firm's productive capacity. With the same workers, the same machines, and the same hours, the business may be able to produce more than before. That can happen because the process runs faster, defects fall, or downtime is reduced. In economic terms, the firm's practical production frontier shifts outward. This is not just about cost cutting, it is about changing what the system is capable of delivering. When an innovation does that consistently, it creates a deeper advantage than a temporary boost in activity. A common pattern is that productivity dips before it improves. Workers need training, workflows have to be redesigned, equipment may need calibration, and early quality problems are common. So the first few months after an innovation is introduced can look disappointing. That does not automatically mean the project failed. In many cases, the short-term decline is part of the learning process that eventually leads to better results. Investors should be careful not to judge too early, especially when the business is still absorbing the change and building operating discipline around it. A disciplined rollout helps separate real innovation from expensive distraction. The process usually starts by identifying the main bottleneck, because an innovation that does not target the constraint may produce weak results. From there, the fix should match the problem and the baseline should be measured before any changes are made. Piloting the innovation on a small scale allows the business to learn without multiplying mistakes across the whole operation. Only after results stabilize should the company expand the change more broadly. This sequence improves the odds that a promising idea becomes a measurable gain rather than a costly experiment. Innovation should be measured with more than one metric. A company might increase units per hour and celebrate a productivity win, while defects, downtime, energy use, or maintenance costs quietly get worse. In that case, the apparent gain may be narrower than it looks. This is why it helps to track output, labor productivity, quality, uptime, and resource use together. Total factor productivity is especially useful when possible because it captures more of the full input picture. The broader lesson is simple. One strong number can hide wider losses if you do not look across the system. This textile mill pilot is a good example of early innovation results. The company was trying to reduce setup time when changing patterns, and the old process took 90 minutes per change. With 10 changes per week, that meant 15 hours were being spent just on setup. The pilot cut setup time to 12 minutes, which is a dramatic process improvement. Yet output only rose from 50 TOWs to 52,000 yards at first. That modest output gain makes sense because large time savings do not always translate immediately into full production gains while people are still learning the new method. Once the textile mill learned the new process and stabilized it, the payoff became much clearer. Setup time fell further to 10 minutes, weaving time increased, and output rose to 80 yards. Defects also dropped by 0.4%, which means the improvement was not just more volume, but better usable output. This is a strong example of why early pilot results can understate long-term value. A process innovation first removed waste, then the organization learned how to capture the free capacity. For investors, this is exactly the kind of pattern that separates a temporary experiment from a real productivity breakthrough. Innovation deserves enthusiasm, but it also deserves caution. R&D spending and equipment purchases have opportunity cost, so money tied up in one project cannot be used elsewhere. If the innovation is poorly matched to the real bottleneck, the company may spend heavily without improving the true constraint. Premature scaling adds another risk because it can spread errors, quality issues, or weak processes across the organization. Some unproven changes simply add cost without creating measurable gains. That is why investors should reward results, not spending alone, and ask whether innovation is translating into better economics. A practical way to test your own thinking is to choose a repetitive task you know well and examine it like a process innovator. Start with something done at least a couple of times each week, because repetition makes waste easier to observe. Then identify the step that causes the biggest delay or friction. A good improvement idea is one that sharply reduces that specific delay rather than trying to redesign everything at once. After that, estimate the likely payback time and name one major risk, such as training needs, quality concerns, or implementation complexity. This habit builds the same kind of disciplined reasoning investors use when judging innovation claims. Section 5. Efficiency metrics. High output by itself does not tell you much about efficiency. Two factories can each produce 100 units, yet one may use far less labor, machine time, materials, and energy than the other. Efficiency adds that missing context by relating output to input. That distinction matters because impressive production can still be expensive, wasteful, or hard to sustain. Investors care about the amount of value created from scarce resources, not just the size of the output number. So when you hear that production is up, the follow-up question should always be, at what resource cost? Efficiency matters because it helps explain whether production strength is translating into better economics. The same output can come from very different levels of waste, downtime, and defect rates. A more efficient plant usually gets more usable output from its resources, which supports lower unit cost and often better margins. It may also be more resilient, since fewer disruptions and less waste make operations easier to scale. For investors, efficiency is often where operating quality shows up before it fully appears in profits. Strong output is good, but strong output with disciplined resource use is much better. Different efficiency metrics reveal different parts of the operating system. Overall equipment effectiveness, or OEE, focuses on how well machines or production lines are actually used. Labor efficiency ratio, or LER, looks at labor time used versus labor time that should have been needed. Cycle time efficiency, or CTE, measures how much of total elapsed time is actually value-adding. Each metric answers a different question about equipment, labor, or process flow. That is why no single measure tells the whole story, and choosing the right one depends on what you are trying to understand. OEE is a widely used metric for equipment effectiveness because it combines three important dimensions. Availability asks whether the machine was running when it was scheduled to run. Performance asks whether it ran at its ideal speed while operating. Quality asks what share of total output was actually good output. Multiplying those three parts gives a single OEE score that summarizes how much planned production time turned into good output at the right speed. A line can lose effectiveness through downtime, slow cycles, or defects, and OEE captures all three in one framework. The score is useful, but it is still a diagnostic measure, not a complete judgment of business success. LE and CTE extend the analysis beyond machines. Labor efficiency ratio compares standard labor hours for good output with the actual labor hours used, so it highlights whether labor is being consumed efficiently. A ratio below 1.0 suggests excess labor use, though the cause may be process problems rather than worker effort. Cycle time efficiency looks at value-added time relative to total cycle time, which makes it especially useful for spotting waiting, movement, and delays. In many real processes, only a small share of elapsed time actually creates value. Together, these metrics help show whether waste is coming from labor usage, process flow, or both. The right efficiency metric starts with the real constraint. If output is limited by machine or line, OEE is often the best place to look because downtime, speed loss, and quality loss directly affect capacity. If labor is scarce, expensive, or central to the operation, labor efficiency measures may be more informative. Measuring the wrong thing can produce bad decisions. A company might focus on labor while machine downtime is the real bottleneck, or focus on equipment while staffing instability is the bigger issue. Good analysis always asks what resource is actually limiting output before choosing the metric. Efficiency metrics are only as reliable as the data behind them. One of the most common mistakes is counting all output as if it were good output, even when part of it is defective. For OEE, you need clean data on planned time, operating time, ideal speed, total units, and defects. For labor efficiency, you need actual labor hours and standard hours based only on good output. For cycle time efficiency, you need a clear separation between value-added time and total elapsed time. Careful definitions matter, because sloppy data can make an operation look healthier than it really is. This worked OEE example shows how the components come together. A packaging line has 480 planned minutes and runs for 450. So availability is 450 divided by 480, or 93, 75%. At an ideal speed of 60 units per minute, those 450 operating minutes could have produced 27, that's in 000 units, but actual output was 24, that's in 000 units. 89%. Of those 24, W notes 1, 200 were defective, leaving 22 800 good units, so quality is 95%. Multiplying the three components gives an OEE of roughly 79, 2%. The score tells you there is meaningful loss in the system, and in this case, the weakest component is performance. Efficiency metrics need careful interpretation because strong scores can still hide business problems. High OEE may simply mean a line is producing efficiently even though demand is weak and inventory is piling up. High labor efficiency can come at the cost of burnout, unsafe pacing, or rising defects. Higher cycle efficiency can also be misleading if steps are cut in ways that damage quality. This is why efficiency should be compared with history, process capability, and relevant peers rather than treated as an absolute success measure. Metrics help locate waste, but they do not replace judgment about the broader business context. The main takeaway is that efficiency metrics are diagnostic tools, not goals in themselves. They are most useful when they help you identify causes and improve the process behind the number. That means counting good output, being careful when comparing unlike machines or jobs, and avoiding targets that ignore operating context. Chasing a score alone often leads to distorted behavior, like pushing speed while quality slips or hiding problems to protect the metric. The better approach is to use the metric as a clue, investigate the cause, and fix the underlying process. That is how efficiency improvements become real economic gains rather than dashboard cosmetics.